Well, welcome back to our course on system engineering. We're continuing to progress through the second section. So we've covered an introduction and some basic knowledge. Last lecture, we talked about the requirements and the defining of the design problem. And now we're going to be getting into more details of the design and integration. First of all, getting into the design. So you need to have the requirements first, and then you can start to do the multi-step part of the architectural process. And so this chapter here, we're going to be talking about the functional architectural development. So for an overview of what is contained in the chapter, we'll be talking about the definition of a functional, physical, and allocated architecture. And so these will be things that we'll explore in details as we go through chapter 7 through 9. This chapter, we're going to be talking about the functional, and so we're going to begin with defining several things that are needed to enable meaningful discussions of the topic. The notion of a functional architecture is designed, and we will also emphasize the idea of process modeling. And so really modeling, there's a lot of different ways you can interpret what modeling means. And so one of the things we'll be talking about is how you model the process. Additional representation is presented in chapter 3 and 12 on data and behavioral modeling methods. And so you can keep that as mind. You can reflect back on what we covered in chapter 3, and we'll be coming back to some of this in chapter 12 as well. So what we're going to be talking about here, specifically for chapter 7, is a modeling approach for partitioning a function into segments. And so you might remember some of these words, a partition and a function, when we talked about discrete math, and in some regards when we got into graph theory in the last major section. So key topics are feedback and control within the functional decomposition, evaluating the architecture for shortfalls and overlaps. So a couple things. How do we do the feedback and control? How do we evaluate for shortfalls and overlaps? So for a really good partition, you don't want to have overlaps. So this chapter will also address the functionality needed for error detection and recovery. So that would be toward the end of the chapter, as well as tracing the input and output requirements to functions and items. Traceability is important, and so what's going to start to be showing up here as we begin to have that discussion. So this is a figure from a practical guide to Sysml, and this is in regards to talking about an example of refining the relationship applied to requirements. So up in the top, we have a requirements Sysml diagram, and at the bottom, we have a state machine Sysml diagram. And so here we're talking about an all-weather system that is capable of detecting intruders under all weather. And so that's the most general requirement that we have. It's derived from a sensor decision. It's verified by, say, here where we have a specific test and we're talking about it, a water spray test, trying to give a challenging environment. And it's refined by the detection scenario and a weather model. And so here we have some of those things, the detection scenario and the weather model. So that's on top, and a state machine is trying to list the control states of a system and what it would actually have. And so here for an all-weather detection of intruder system, we need to be able to deal with cloudy, rainy, snowy, and foggy, as well as clear. And so here is how we go from one state to another in terms of migrating, first of all, between clear and not clear, and then the more specific areas and how we would have more sophistication in our functional architecture if we're trying to address one of those more specific states. So here in terms of terminology that we'll be starting to need for this architecture development, we have modes, we have state of the system, function, and functionality. So mode is a distinct operating capability of the system during which some or all of the system's functions may be performed to a full or limited degree. An operational mode, a test mode, A power savings mode, you can think of stuff like that. A state of a system is a static snapshot of the set of metrics or variables needed to describe fully the system's capability to perform the system's functions. A function is a process that takes inputs and transforms into outputs. And you can be thinking of this as like a black box. And so there's an input and an output. We've looked at it in a couple different ways. Functionality is a set of functions that is required to produce a particular output. And so we can either have simple functionality or complete functionality. So simple functionality is an ordered sequence of functional processes that operates on a single input to produce a specific output. And a complete set of complete functionality is a complete set of coordinated process that operates all of the necessary inputs for producing a specific output. So what is a functional architecture? It is a logical architecture that defines what the system must do. And so a decomposition of the system's top level function is where we start to be figuring this out. This very limited definition of the functional architecture is the most common and is represented as a directed tree. And we talked a little bit about that when we talked about graph theory. A logical mode that captures the transformation inputs to outputs using the control information. So that's another characteristic of a functional architecture. So this adds to the flow of inputs to outputs through the functional decomposition. And we'll get into this more in chapter 12. We're not focusing on IDF0, but you'll see in the Booty textbook that they'll be talking about that a lot. And finally, functional architecture is a logical model of the functional decomposition plus the flow of inputs and outputs, to which the inputs and outputs requirements have been traced to specific function and items. So how does this start to look? We have an IDF0 view, which will come in the next chart, but here we're using a Sysml block definition diagram. And so we have this flow from the define the functions for ConOps. We evaluate the functional model. There's the ability to iterate, and finally we trace the requirements to the functions. And so this is what we have laid out here. There's a lot of developmental steps that are here, and there's inputs and outputs, and finally we develop a system level functional architecture is what the goal is. So that's one possible way of viewing it from a Sysml point of view. And in an IDF0 point of view, you can see this sort of this waterfall process. You have your inputs on the left, you have your outputs on the right, and the things that each module feeds into from previous modules. And so take your pick in some ways, but those are two alternative ways of how we start to capture what a functional architecture process is. And so let's talk about decomposition versus composition. So this is where we're talking about either going a top down or a bottom up. So if we're doing a top down, then it's decomposition. So we're partitioning system functions at a level at a time. And this needs to have a sound definition of all inputs and outputs. On the flip side, if we have a composition, this is a bottom up. And so this way we define many functionalities from a bottom level point of view, and we synthesize the functional hierarchy from many bottom level functions. And so maybe this might be there's certain technologies and enablers, things that maybe you know that you want to make sure that you leverage in your design, so that may be pushing things up, versus a decomposition. This could be led largely by the stakeholders or customers. And in reality, you're going to be using both to form the best solution. Well, let's talk about how we define the functional partitions, and we'll show some examples of how that would work. So we need to use the operating modes, we need to use the inputs, we need to use the inputs and controls, and use the stimulus and response threads. So we have to identify what these are. And then we can be doing a functional decomposition. Booty talks about what he calls, from research that now has been done a while ago, the Hatley-Pribhai template. And so whatever you want to be thinking about it, there is a functional decomposition process. We'll talk about a, quote, living systems template. using analogies towards what you might be thinking of a living ecosystem. And then we'll talk about the segments of how to put these segments into fundamental and custodial groupings. So here are a couple of definitions from the textbook before we get into an illustration of what this might look like. Notionally is you need to have the provider user interface. So this is how you request, have the function to request and obtain user inputs. You want to have the ability to format inputs. There may be a format that was used externally and it has to be translated to what's used internally, and to identify if there's unintended inputs and to not pass those on. You want to have the whole process of transforming the inputs to the outputs. And so this is this would be aggregating the major function of the systems. There needs to be control processing where functions needed to control resources or the order in which these processing functions should be occurred. And finally, formatting the outputs. And so you may have an interface such that you need to put it into a different standard or different way of presenting that data. So those are the kind of generic functions that need to be addressed in a functional architecture. So here is an illustration of capturing those things that I just mentioned. You have the input processing, the output processing, the user interface processing. You have to be talking about process and control. And so we talked about that already in the previous chart, but this is gives an illustration of a template of what it might look like. And then if we wanted to do a functional decomposition, at least using this strategy with this template, we can be breaking it down into logical parts. And so you have one or more functions that need to be done by a system. Whatever analogy you want to be using it, a satellite could be thinking about sensor processing, bus processing, bus information, telemetry and commanding processing. And so you can be parsing all of those things into smaller elements that feed into, say, a larger construct. So this middle part of this template could be the higher level functions, and then you have lower level functions that feed into that. So that would be an example of something that you could be doing with a functional decomposition. We have this elevator example that we keep coming back to. And so here would be a way that you could be talking about that it accepts passengers, requests and provides feedback. It has the ability to move passengers between floors and control the elevator cars, enable effective maintenance and services. And so these are all the things that would need to be captured using like what we're showing in this template. We're seeing a specific example for an elevator. Well, now let's talk about another example, and this is with living system, and there'll be 3 charts that we'll be showing. So you first of all, we'll talk about the subsystems that process both matter, energy, and information. And some of these terms would be things that you'd be more familiar with from thinking about a living system. For reproduction as an example, something that's common for a living system. So reproducer is a system that is capable of giving rise to other systems similar to the one that it is in. So you can think of that maybe from a variety of different points of view. Maybe some software package, it creates a new instance to have extensibility and do more things in parallel. Maybe the way a system is designed that you bring in more hardware elements because there's more required to process, or the way that you're figuring out how you're going to be storing information. For a boundary, this is the subsystem at the perimeter of the system that holds together the components to make sure that the system protects them from environmental stresses and other types of stresses that might take place. So that's the matter, energy, and information. And then breaking it down, here are some specific things that would be related to matter energy. So thinking in terms of a living system, doing ingestion, and so you can be thinking of taking in nutrients and how you process that. And so there's ingestion, there's energy storage, There's the ability of converting, say, whatever type of nutrients into the type of format that's needed internally. And so you have an ingester, you have an ability to distribute, carry it to various parts of the system, you have ability to convert things from one form to another. You're able to produce the things that are necessary. So this could be maybe you need to do repair or growth or replacement of components. Those are all things that would be familiar with what you would think from a living system. There's a storage, and so there's ability to retain in the system for a period of time, deposit various sorts of matter energy. The extruder, this is the amount, the ability for the system to be able to expel byproducts that are no longer needed for the system. The motor, this is the ability to have propulsion and movement, and so you're able to energize and to do work with the system. Finally, the supporter, this is a subsystem that maintains a proper spatial relationship among components. And so a conductor, if you will, that makes sure that everything is operating efficiently. So that's the second part. And then we're moving on to the parts that are focused on information. And so information flow, memory, decoding, a lot of different things are part of this. And so you need to have the ability to handle the input, the sensory subsystems to take in information. There's in the internal transducer, the sensory subsystem that receives from the subsystems or components within the system, markers bearing information about the significant alterations in those subsystems or components. You can have multiple channels and a network that has a ability to have components to be interconnected. So there's the ability to have communication. There's the decoding. And so you can have encryption. You can have various ways of trying to have efficiency and passing information from one point to another. You can have an associator, that this is the subsystem that carries out the first stage of the learning process, forming enduring associations. And so you're able to learn and recall and repeat things that have been encountered. There's a memory, so you have the ability to store various sorts of information. There's a decider, and so you have a control function that an executive that is able to take in information and make decisions, pre-programmed outcomes based on certain inputs. There is the encoder. So we have the decoder to process information. And then as things are going out, we have the ability to encode it and to create a quote private code to send things externally. And finally, the output transducer. This is a system that puts out markers, bearings, information from the system, changing markers within the system into other matter energy forms, which can then be transmitted over channels in the system's environment. So a little bit lengthy there, but we're seeing another example of a template that we could be using for creating a functional architecture. We talked about it earlier that there needs to be feedback and control in a functional design. And so we're doing things at a block level. And so here is a basic processing, an input and an output, and you have a black box. You can have a open loop control of process. And so you have what is the desired output. You have the control process that helps you to ensure that you get that. So that would be one possibility. Another common thing is you have this feedback. And so you have a closed loop control that you actually produce a result. And then you can be providing feedback are you on target or are you not on target? And if you're not on target, giving the information that can be fed into the control process to go back to the more in line with what you would like to have for this overall process. So using the Sysml, here is a way of how we can be capturing the feedback control and operational architecture development. And I'll show the IDEF0 in the next chart. So we have a waterfall of events. You allocate the functions and system-wide requirements to the physical subsystem. You define and analyze functional activation and control structures. that is then passed on to conduct performance and risk analysis. With that, you are able to document the architecture and obtain approval. And finally, you document the subsystem specification. And using an IDEF0, you see that the same blocks that I just mentioned and have a more detail in terms of the connectivities, the inputs and outputs for this overall process. What about the evaluation of a functional hierarchy? So you want to be looking to see if there's any shortfalls, or is there an absence of functionality? Is there an absence of functionality for the input set? Is there an inability to produce the desired outputs? Is there insufficient feedback and control to produce the desired output? So those are the things you want to be looking at. Are there overlaps? Remember when we talked in discrete mathematics about partitions, and you want to make sure that there are no overlaps. An overlap would call a redundancy and functionality, and so you could have ambiguity in how the overall system is going to operate. And then you want to be doing evaluation analysis. And so an evaluation technique is to use scenarios and to trace those scenarios and see how things work in various ways of what's supposed to happen. So here's just a single chart for an activity diagram showing the flow for a scenario. So you provide a service, you accept inputs, accept the tasking, perform the tasking, maintain the system, and complete tasking. And so you can think of an elevator example that's probably clear to do that, but really for any system, you can have this type of a flow. And as we're just now dealing with a functional architecture, this is really adequate. And so now we are focusing on the elevator, and I'm not going to go through it in details, but each one of these charts is another IDEF0 that's walking through this multi-phase step process that I showed you in this activity diagram when I showed you the Sysml approach. So we want to be providing the service. We want to be accepting the inputs. And so that's the kind of connectivity that would be needed to ensure that. We want to be accept the tasking. So the tasking is to receive and transport a passenger. You actually perform the tasking, the movement of the passenger from one floor to another. You want to have the ability to monitor the system so that you can see that things are done in the proper fashion, and finally report back that you have completed the tasking and you now are ready to do additional tasking. Well, let's talk about some common mistakes. You can include external systems and their functions, and so you need to have this decoupling of what you are responsible versus what someone else is responsible for. The functional architecture only addresses the top level function of the system in question. So you want to make sure that you don't get that mixed up. Choosing the wrong name for a function. The function name should start with an action verb and include an object of that action. So this would be an important thing that you want to be monitoring as you're doing your functional decomposition. Creating a decomposition of the functions that is not a partition of that function. So you want to, once again, make sure that you're staying in bounds with what you're meant to do. The sub-functions of a function should all be the same level of abstraction. That's another important thing. And here's just a listing of the types of what you could be doing for decomposition. And so I'm not going to read through that. And so here, this would be, for example, a student wants to decompose. You have these things, and you can just walk through that at your leisure. You can stop the lecture, read the lecture notes, or view this in the textbook. Continuing on, you can be including a verb phrase as part of the inputs or the controls or the outputs of the function. Verb phrases are reserved for functions. You could violate the law of conservation of input controls and inputs. That is, every input and output control of a particular function must appear on the decomposition of that function, and there can be no new ones. There could be trivializing the richness of interaction between the functions that decompose their parents. You could be wanting to create an input from thin air. There has to be something that's very clear. There's an input and their output. And so the most common mistake is to define a function that monitors the system status, but that does not receive inputs about the function or lack of functionality of other parts of the system. All right, well, let's talk about fault tolerance. And so we'll have a handful of charts that start to get into this detail. This would make sense from a functional point of view, because this could be something that would impact your more detailed development of a system design. So here are some definitions. In this context, a system is an identifiable mechanism that maintains a pattern of behavior at the interface between the system and its environment. A failure is a deviation of behavior from the system and its requirement. An error is a subsystem of the system states which may lead to a failure. And finally, a fault is a defect in the system that may cause an error. There's more details there, but I was just trying to summarize some of those details. So what are fault tolerance functions? And here we're talking about 4. First of all, you need to do an error detection before you can do anything about that. Once you do an error detection, you can do a damage confinement. So you don't want to continue to propagate and cause more damage. That would be a great way to be something you would want to include in a fault tolerance functionality. You want to do error recovery so that you can go back to a normal state. And finally, the fault isolation and reporting. You want to have an exhaustive debug set of information that's passed on. So hopefully you can work through that so it doesn't happen again. Maybe you can update the architecture or some part if you're able to have access to the system, or perhaps maybe configure a new piece of hardware that's already available, or something else. Those are some possibilities. So here is a concept map for fault tolerance. And so you can see whatever way you might want to be thinking about this, that this is a directed graph, but we're trying to capture all of these various things and the relationships. So a system has requirements, a system has states, state has substates, a system may have a defect, and the defect may be a fault. And so here we can just see that there's a useful flow of all the possibilities that you could walk through on this chart. What about tracing of requirements? And so a table is a great way to be doing this. And so if you have an X, you can see that there's a tracing of here providing an elevator surface. And so there's a connection with the elevator system shall receive calls for up and down service from all floors of the building. And so we can just see how we have these checks that go from one function and relate those to one of these 4 categories or multiple ones of those categories of requirements. All right, well, that's a short introduction to functional architecture. Thank you very much.